Hi, this is Joe Macios from AE Tutoring Enterprises. Today I want to talk about how to use and take advantage of function notation in the Apple Grapher. Let's go ahead and jump over to the Grapher. I've got a window set up already. We're going to take a look at a particular equation to help us today, and that equation is y equals sine of x. For those of you in pre-calculus, you're probably getting familiar with this equation. So we're going to take a look at this and see what we can do with it. First of all, I want you to notice that this is a equation where we have pi right here and 2 pi right here. So this is in radian mode. And we're going to set this up so that this is a function. Now to do that, we're going to change this, the y in this, to f of x. Now doing that lets the calculator know that we're defining a function. And you'll see two things that have just happened here. The graph disappeared for number one. And number two, the little checkbox got replaced with this little green equal sign, which tells us that this is a definition. So we're defining f of x to be sine of x. All right, the other thing then we can get to bring back that equation to get the graph back is to simply set y equal to f of x. When we hit return there, we get our graph back. Now you may be wondering, why do we want to go through writing out two equations in order to get done what we could have done with one equation? Well, keep hanging in there and you're going to see some reasons for it. One of the things that we can do with this right now is think of this sine of x as a parent function. And you might remember through either your geometry or advanced algebra, or even maybe some of the things you're doing in pre-calc now, that you can use a parent function to generate any other curve that is in the same family as that parent. So for example, I can take this sine of x and define another variable. Let me define h to be 0 for right now. And then I can come over here and put in minus h. Now some of you already know what that's going to do, and if you don't, well, it'll only take a moment or two for you to figure it out. Let me animate the h. I've done that by highlighting the h equals 0 and then coming to animate this parameter. And I'm going to choose various values. The values I'm going to choose, I'm going to make it kind of small. So negative 0.5 to 0.5. And let's go by 41 values. That'll pick the speed up a little bit. And we're just going to go ahead and hit play and see what happens. Okay. So right now, h is becoming more negative and it's shifting to the left. And now it's becoming more positive and it's shifting back to the right. It's just passing 0, and so now this is the sine curve moving into the positive x direction. Here, this point is eventually going to get right to here. That's 0, and now it's moving into the negative x direction when h is negative. So basically, h is responsible for shifting it back and forth, left and right. Okay. Let's go ahead and stop that. Now I'm going to go ahead and change this variable to something else, like an a. And notice that that'll actually automatically change it up there, but I'm actually going to change what this is doing now. I'm going to call this x divided by a. And it's not going to really be happy with that because I'm taking x and I'm dividing it by 0, so that's why the graph just disappeared. But let's go ahead and animate the parameter again. And wow, that actually kept the right values. But let me make this go from -2 to 2. And let's go see what this is going to do. Let's hit OK. And let's play. All right, so you can see as h is getting bigger, it's basically stretching out the sine curve. There's 1 where it was normal. Now it's beginning to become smaller. Well, actually, it did that pretty darn quick. Let me pause this and actually give us a little more steps to see this. I'll slow it down a little bit. Okay, so here it is getting closer to 0, and once it gets to 0, it's undefined, so it's just completely squeezed, if you will, into the y-axis, and it doesn't really know what to do with that, so it just doesn't do anything. But here it is stretching it out again, bringing it back down. So as a gets closer to 0, it gets more compressed. When it's negative, it's actually flipping the entire graph about the y-axis and stretching it from there. So that's what this is doing. Now notice that in both cases we never played with the f of x function. The f of x stayed sine of x. So we were using this function notation to see what was happening as we would simply replace every x with x over a, for example. All right. Well, I think that gives you a pretty good idea of at least one thing you can do with your function notation. So let me stop that. I'm going to need to get rid of this little a for the moment. And let me get rid of that. Okay. Now, another thing that you might be doing in your pre-calc class or trig class is you might be using degrees rather than using radians. So what I'd like to do is write a function. Now, since this function built into the calculator is automatically in radians, we have to do something in order to use degrees. And what we're going to do is we're going to define another function to do that. So let me call this new function u of x, and we're going to put in pi over 180 times x. So for example, if I put in 360 degrees for x, 360 divided by 180 is going to be 2, and we will get 2 pi. And that's what then we can use in the f of x to help us graph this in degrees. Okay, so let me hit return there. There's our function definition again. Let me move this down here. And now all I'm going to do is let me click on it again, and I'm going to replace my x with u of x. And it looks a little strange now because it's been stretched out, but let me go ahead and go to View and then Frame Limits, and then I can choose appropriate x values. Let's go from minus 10 degrees to about 400 degrees. And I think the negative 3 to 3 is good enough for the y. And there it is again. So now you've seen a sort of a secondary type of thing, and I guess I could ask you what this is called, but you're not going to be able to answer me. This is called a composite function, and that's also something you're going to learn about. If not in pre-calculus, you're certainly going to learn about it in calculus. By the way, if you're curious as to what you're really going to do with a composite function in calculus, at least for me, the main idea behind a composite function is the chain rule. So if you're in calculus and you're looking at this, you should be thinking chain rule. That's why they spend a lot of time teaching you composite functions. All right. Well, this is not the only thing we can do. I mean, this is another good reason to do what we're doing. Again, we're still using f of x. We've got our conversion factor. That's effectively what that is, defined separate from the original function. And by the way, then we could use this conversion factor in, like, say, a g of x, for example. Let's go ahead and do a g of x. G of x is equal to cosine of x. And then we could plot another y is equal to g of u of x. And there would be our cosine function in degrees. Okay. Well, I'm not real happy about dealing with that right now. Let me go ahead and deal a little bit more with some of the things that we can do with the sine of x. What I'm going to do is plot a bunch of points, and I'm going to use the same function to help me do that. And I'm going to start by naming the points that I want to talk about. Now, in the last video, I talked about the idea that we can use parameters that take on very specific discrete values, and the notation for that was this set notation, if you will. So we're going to let a equal 0, 30 degrees, 60 degrees, and so on, all the way to 360 degrees. Okay. All right, and now we're going to pull up a point. So we're going to come down to a new equation from the template, the parametric tab, the Cartesian curve. We're going to get rid of the parametric part of this because we're plotting points. And I'm going to put some spaces in there. And now what we're going to do is we're going to tell it that we want on the x-axis to graph every a, and in correspondence with that a, we want to graph f of u of a. Let's hit return to see what happens. Well, that was pretty darn easy. We got a whole bunch of points, and these are all the points that are on the unit circle. Of course, it doesn't look like a circle here to us, but there it is. Let's go ahead and clean this up a little bit. Let's come over to here and turn off the polygon, and I'm going to make fill in the circles and make the circles a little smaller. And then we have our little graph. All right, let's also come over to here and change the color of our graph to match the color of our points. Or they can be different. It's your choice, your graph. Okay, but there it is. There's another advantage of that. So what you're now seeing, and let me point this out, is that here's f of x, and here's u of x. And it's fairly complicated that what I'm graphing is f of u of x. Now that's not only the graph, it's also these points. And I can use these in further calculations. For example, I could go ahead and do things like take derivatives and use these in those derivatives, evaluating points and so on and so forth. I can find the tangent to a curve and all kinds of fun stuff. And by having this f of x defined, it stops you from having to keep typing in sine of pi over 180 times x over and over and over and over again. So there's a big advantage to doing it this way. Well, that's it for function notation. Clearly there's more that could be done. I just wanted to give you a little taste of what you could do, and I've given you sort of 3 good reasons why function notation can be a useful thing. You need to probably practice it a little bit before you become comfortable with it, but it's worth the time and effort to play around with it. There's also some demos that actually use function notation or examples. I should have probably looked ahead of time to know which ones they were. And I don't know which one it's going to be. Maybe periodic functions. Let's see. Yeah, they're using, oh, they've even used a little colon there with the equal sign. Interesting. I guess that's not necessary, but they were using it. This is a nice little example of showing you pieces of functions and so forth, and a lot of different things that are being used here. There's a few extra things here that they're talking about, mod functions and so forth, modulo operator. And so a lot of the stuff that I learned came from just simply looking and examining and playing with some of the examples. You may want to do that yourself. So that's a whole bunch of examples, but definitely they're using functions here. So that was a pretty good guess. Generally, I don't try to save these because I want the original functions as they were. So if I were going to mess with this and then, in fact, before you mess with this, you probably ought to resave this as a file under your own name and then, or a name of your choosing, and then play with this stuff. All right. Well, that's it for this graph on functions. Let's get back over to the final screens. Again, this was how to use and take advantage of some function notation. Save yourself some effort. My little business is A Tutoring Enterprises. My name is Joe Maciars. My website is at www.tutent.com. My email address is tutent@neb.rr.com, and my phone number is 402-421-3536. I do online tutoring for anybody that's interested in the world, and I also do in-person tutoring in Lincoln, Nebraska. I have my hours and my prices and all kinds of good information on my website. Please check that out. And we're going to now scroll down to a screen where hopefully you'll see a whole bunch of links coming up that are talking about all the how-to videos. If you like the video, please feel free to go down and hit the little like button. I always appreciate that, and I appreciate you watching, and I hope you get to watch more of my videos. Thanks.